Yeah, thanks a lot for having me. Thanks a lot for the invitation. I'm actually a user of ESO telescopes. I'm one of the power users, so to say, because I'm traveling roughly like 3 to 5 times a year to Parnell to observe there. So I'm going a bit further north than the Gemini South telescopes. And what we do there is interferometry. Yet I'm here to report also on observations which we did with Gemini, and you'll see in a second why actually we very much wanted that. It's probably everybody is aware of these beautiful observations which adaptive optics have given to us from the center of the Milky Way. You can see here a very simple technique, namely you take 16 images, each a year apart, you plug them behind each other, and you can see beautifully how the stars are revolving around that red cross, and that red cross of course marks the position of Sag A star, the supermassive black hole candidate in the Milky Way. The star, which is labeled S2, is you'll see is the most important one, and everybody knows of course that this was given to the led to the Nobel Prize. The experimental part of the 2020 Nobel Prize was given to Andrea Ghez and Reinhard Genzel, and Reinhard Genzel actually pays my salary, so I'm part of his team. So you can see here, I was invited when he was given the medal. It was not in Stockholm, it was in Bavaria, in Munich. The Swedish ambassador spoke on behalf of the king. Nevertheless, we are invited to go to Stockholm end of this year. So let's see if that will happen. So let me start by saying that actually in the Galactic Centre, it's really observationally, it's source confusion, which is the limiting factor. If you don't use adaptive optics, your telescope is as good as lambda divided by the atmospheric coherence turbulence cell size, R0, the Fried parameter. And this is typically 40 centimeters, so your resolution is even at an 8-meter telescope limited to something like 1 arcsecond. Doing adaptive optics, you can improve here by a factor around 20 or so, because then you get sharp across the aperture and you get a resolution of around 50 to 60 milliarcseconds. However, if you are able to do interferometry on Parnell, or if you could also do it on Mauna Kea, you have baselines of hundreds of meter, 120 meter in the case of Parnell. And you see, you gain another factor of 15 compared to the 8-meter. So this is, of course, a huge, huge factor. So for almost 20 years, we had 2 AO workhorse instruments at the VLT. One was NACO, operating from 2002 to 2019. And one was Symphony, operating from 2003 to 2019. And you can see here the problem. The schedule when to recommission new instruments was not taking into account COVID. And that's why we had a data gap, and that's why we reached out to Gemini, whether we actually could not use their telescopes in 2021, and you'll see how beautifully that has worked. But let me first talk a bit about our interferometric project. So here you can see the mountain Parnell. And one way to think of an interferometer is, I mean, okay, we have beautiful 8-meter telescopes, but how beautifully would look that mountain if it were completely covered with a mirror, a 130-meter mirror? And if you have such a mirror, it's obviously you get a very sharp image. And if you now start dropping a bit of black paint onto that mirror, it will not matter, right? A bucket of black paint here and there will just look like a bit of dirt on that mirror. And you can put more and more black paint on the mirror until you have only 4 apertures left. And the only thing which you need to do is you have to combine the light of these 4 apertures in a way as if they were a single mirror. And that's the technique called interferometry. What it gets you is typically fringes, and these are characterized by a phase and a visibility, and these phases and visibilities vary as a function of your baseline length. And the baseline length, again, is also given by not only the baseline, but also the wavelength you're observing. So by observing a different wavelengths, you can also change the wavelength. And you can see here a beautiful example of such a signature. You can see very, very strong signatures, and you can describe actually the signatures you see here with a simple model, with a binary model. And for that, you have source parameters, maybe, for example, a separation vector, a brightness ratio, the source colors, and you need to know a bit about your instrument, so like bandwidth smearing or the injection per telescope, so telescope-dependent parameters. However, if you do that a few times in the night, you get more and more of these things, then you can actually collect enough information that you can do the Fourier inverse transform, and you can reconstruct actually an image. So typically with one night of data, one can reconstruct the image, and here you can see how that model actually looked like. It was the star S2 and the source such a star itself. The elongation of the sources is the interferometric beam. This is sort of say the price one pays for the fact that our we don't have a full aperture, we don't get a nice beam, we get a dirty beam, so to say. And one really should say that laser guide star adaptive optics is really 15 times less sharp. So it sounds great to do laser guide star adaptive optics, but it's not particularly sharp in that sense. And even if you go to the next generation telescopes, the 30 to 40 meters, they're still a factor 3 to 4 less sharp than what interferometry does now routinely. And you can see here the stellar field as it looks like with adaptive optics on the left. In the middle, you can see a zoom in onto the central region where Sag star is the circle and S2 is the star up. And on the right-hand side, you can see the same field, how it looks with interferometry. And it's obvious that no way that you can distinguish all these individual stars with the adaptive optics. It's maybe also interesting to compare the UV coverage, so how well we actually sample, how well we synthesize a mirror. And we compare it here to the EHT, which of course you have seen the Event Horizon Telescope image. And you can see we have only 6 baselines for telescopes, much less than what the EHT was using, but we are actually using the full K-band. So that is from 2.0 to 2.4 microns. This is a 20% bandwidth, so to say. And this is of course unheard of in radio astronomy. And that's why actually our UV strikes are not only dots, but they're actually really bands, as you can see. And you can imagine that this doesn't give you too bad of a coverage. Here you can see the orbit which we've reconstructed. You can see that we've started in 1992. That was up here. The star went down through Pericenter in 2002. Then adaptive optics came along. That was what we traced all the way here. And in 2016, the first interferometric point came, and then 2017, 18, 19, 20. In 2020, we got one data point. I recall very vividly that I managed to go home one day before actually the lockdown came. My family arrived also the same day from their vacation. We were all back home, next day lockdown. But the most important point was, of course, the data point was there. And you can see that in 2021, then we switched to remote observations. And here you can see also our latest data from 2022. So the star has a period of 16 years, semi-major axis of 125 milliarc seconds and eccentricity of 0.88. And the typical uncertainties are in the 0.2% regime. So if you think of the angular momentum or energy of the star. And we can also precisely say that the pericenter was on the 19th of May in 2018. And here's the radial velocity data for the star. You can see that the dense sampling actually started after the orbit was discovered. And since the discovery of the orbit was right after pericenter, the first 2 data points obtained with the Keck telescopes, they were sort of at random points. But then one realized that it's important to trace this star. You can see how beautifully we were tracking this star. But you can also see that in 2019, the Symphony series ends. And this is, of course, where the Gemini data points come in. And these points, I'll show later a little bit how we obtained those. The 2022 points are now from the successor instrument ARIES, which is being installed right now. So this is commissioning data. S2 is very fruitful. There's a plentitude of stars, but S2 really stands out. S2 is that orbit here. It is the second shortest. It's not the shortest period. The shortest is 12. But it happens to be the brightest star, so it's actually easiest accessible. And we've done plenty of things. For example, you get a geometric distance. You can think of it, we measure a proper motion and we measure a radial velocity coupled with a simple geometrical model, namely an orbit. So you get a very direct distance measurement, because one is measured in milliarc seconds per year, the other in kilometer per second, and milliarc second to kilometer is the distance. We've measured the relativistic redshift of the light leaving the star. We've seen the precession of the star, the relativistic precession, and we can give limits on the extended mass. On the test of the equivalence principle, I skip for the time reasons. So at closest approach, S2 actually reached 8,000 kilometers per second. Compare that to Earth motion, 30 kilometers per second. And we know that it's mildly relativistic, 2.5% speed of light, but the transverse Doppler effect should show up and the gravitational redshift. Those two terms are actually identical in size for a Keplerian orbit. And if I can show you now how the residuals to the Kepler orbit look like, and you can see here beautifully the redshift signature, which showed up as a 200-kilometer signal. And again, you can see why in 2019 we were reaching out to Gemini, because we really wanted to get those data points here on that side. And you can also see that the new instrument ARIS is now starting to deliver, hopefully, data again. The effect is measured with around 25 sigma, and so that looks much more here in this plot, but this is because you can think of finding a different Kepler orbit which mimics a bit that signature. So that was something which was easily realized in 2006. At the time, people proposed either use two orbits or use hilarious good astrometry, and we did the second thing. We used simply very good astrometry. Also, the Schwarzschild precession is detected. So this is at 8 sigma. So this is the effect that the orbit is precessing progressively. You can see it in this plot. You just have to zoom in a little bit. And you can see here that the star has changed its orbital trace. And here you can see actually the actual data. You can see that the Kepler orbit by now is largely excluded. And the star has really changed its orbital orientation at Pericenter. What is new since 2021 is that actually we're tracing more stars than only S2. So we have actually, you can see here the field in March, May, June, and July observed with gravity, and you can easily draw again like this beautiful orbits through these individual data points. And it happens, of course, that these stars were known to us, so we had previous coverage for those stars, and then you get very quickly beautiful orbits. And you can see here, besides S2, the star S29 seems to be also very interesting. It's also coming close, and it went through Pericenter in 2021. And if I show you now the radial velocity curve, you can see here how deeply that star should dive. And it actually did dive very, very deeply. You can see here this -4, -5,000 kilometers per second. And those two data points, they are from Gemini. So that was the actual reason why we wanted to be in 2021 at the telescope. So let me just report a little bit on using Genius at Gemini North. So I'm a user of ESO, and I have to say that compared to observing at an ESO telescope, where you have the feeling to be in a factory of science, it was very refreshing, warm, and welcoming to observe with Gemini. I really liked it. Where's Jen? Is she already back from lunch? Very, very nice to do that. Very direct. You just zoom into the observations. You talk to the people. You see everything they also see. Who has observed with ESO telescopes here in the room? You recognize the difference in how things are done at the different telescopes. So I found it very, very nice, and I'd like to say thanks a lot for the hospitality. So here's our slit, which we wanted to put. We wanted, of course, to put it on S29, on S2. And it happens that if you do the slit orientation in that way, you also get a bright star here, which you can use for alignment purposes. And you get a moderately bright star also here, which is a well-known late-type star, for which the radial velocity is very easily measured. So this is the best slit orientation we could think of. Here's then the finding chart. You see that actually there's a very bright star, which you miss with the slit. And then you go to the telescope, and hooray, you get your acquisition image. And it looks like just the image before, just rotated by 90 degrees. You have to figure out that. Then comes the through slit image, and you can see here the little dots which are here in the through slit image. This is S2 and S10, so they are there. Here are then the reduced spectra. So this is the whole stack of a night which we obtained. And if you zoom in a little bit, you can see here, this is the S10 spectrum, and this is the S2 spectrum. The wavelength calibration, I didn't even know if there was a pipeline. I think I just did it myself. Very linear relation, you get this thing. And then you can check things, for example, on the star S10. It has CO band heads, so at 2.3 microns, you get these sharp features, which you can easily identify. Here's all the symphony measurements before, and you can see that grossly things seem to work out for also for that star. Notice the scale here. This is only a 50 kilometer per second difference. So S10, here's the Gemini points. For S2, you can see here the spectrum of S2 also works as expected. You've seen that already. There was another star in the slit, S24, also here, CO band heads. And also that star is interesting. It goes through pericenter next year, and it started already curving its radial velocity in 2021. So it's also important to do. And of course, here you can see the spectrum where the bracket gamma line of S29 is. So you see, it's exactly, we didn't overexpose. You needed that integration that is maybe, I don't know if you would trust the line, but of course we had a strong prior where the line should be. Having several orbits, you can then do, of course, a more involved orbit fit. So you then have 7 parameters for the black hole and 6 for each star. You get a huge parameter space, but in the end, you get very small error bars on the level of 0.5% or so. And this really should be said that it's not only S2, it's also S29, which contributes, because also that went very far away in radial velocity, and this gives you a huge lever arm on this plot. And if you put it into context compared to what was done before, you can see here that, of course, this factor 15 in resolution translates into an accuracy here in this plot. We continue as we speak, so we have more stars. You can see here compilation of 2022 orbital traces. S38 is going through pericenter this year. So this is this guy here. S24 will do so next year. And for example, we can conclude from that 99.9% of the mass of such a star needs to be inside of S29's apocenter, which is 100 AU, so Neptune orbit or something like that, which means there's at most a 4,000 solar masses, which could be in any sort of extended configuration. Think of a sea of neutron stars, think of dark matter or something. So we are really probing the black hole nature here very, very well. How far can we get? Well, if we have a star which would come 10 times closer than S2 over 10, then lens steering precession should be in reach. And this is our medium-term goal. So the spin of such a star, it probably requires ELT spectroscopy. We need the big mirror to go down to these faint levels, and the interferometry, maybe another 2 or 3 magnitudes fainter than what we can do now. We're working on that. Even longer term goal would be the no-hair theorem. If you look at the equation of motions, there's then at some point the quadrupole moment in there, and the quadrupole moment relates to the spin of the black hole in general relativity. So if you measure the spin, you can predict the quadrupole moment. If you then can measure it, you can have a check, and this is a first check on the no-hair theorem. So essentially what you need for that is radial velocities with 100 meter per second uncertainty. Currently we are at 7 kilometer per second. And then finally, let me just also report, since the EHT result came out. So in the infrared, such a star itself is a flaring source. Here you see 1 hour of L-band data, and you can see that this outbursts occurs from time to time. One is not able to predict that. Here, adaptive optics data on the same scale, interferometric data, you can see these outbursts. And the speculation really is that this is an analog to solar flares happening on the accretion disk. And if you do simulations of these flares, you find that they actually astrometrically revolve. And the signature should be in the regime of the gravity astrometry, which is a few 10 microarc seconds. And you can see here our proposal from 2006, and here an observation in 2018. And if I overlay that now on the EHT image, you beautifully see that indeed we are seeing things revolve on the right scale. And in 2022, you see here 1 example of a flare which we've just observed, still working on that. Unfortunately, however, we know that such a star is not showing us its spin, but the angular momentum vector one sees in these flares is actually the one of the material feeding it. So you see the spin of the accretion disk, and that is determined by the inflow of stellar winds. So it's not the spin of the black hole, which we can measure in that way. And with that, I'd like to thank you for your attention, and thanks, of course, to the whole Gravity team. You see, it's a huge instrumental team behind this work. Thanks a lot.
Questions for Stefan? Do we have questions on Slack? Well, let me start then. This is a fabulous result, and you showed the power of angular resolution, the power of tracking the orbits over time. It looks like you've got enough light, but to go to the next step, which of the three is the most important? More resolution, more photons, or just more time to track the orbits?
Well, in the end, I think patience beats everything. Yeah. And that's also, it's actually very difficult. You might know this from NSF funding. If you need a continuous flow of time or money or anything, it's always hard to convince that after 6 years, you need year number 7, and then again, year number 8. But for these time series measurements, that's actually very hard. And ESO has this model of guaranteed observing time. Mm-hmm. I don't know if you implement this in Gemini. It's very powerful because that's where we essentially can say, okay, we sell our instrument to ESO and we have the next 10 years of data guaranteed. And that takes away a lot of stress. Without that, we wouldn't be building instruments, I have to say. And instrumentally, I think it's clear. So for the what we're actually doing is to equip all VLTs with laser guide star adaptive optics now, so that improves then the adaptive optics. Then you get more light into the interferometric fibers, and that hopefully brings us deeper in the interferometric images. And once you pick out a star which is close to such a star, it should be very easy to do spectroscopy on it, because if the star is physically close, it will be moving very fast, which means the Doppler shift will be plus 10,000 or minus 10,000. There will be no confusion issue, yes, because it will be moved away so quickly and it will change quickly. And the diameter of the telescope should, of course, allow us to go down to 22nd, 23rd magnitude. In addition, we might, so currently we're seeing O and B stars, and we can go down the main sequence. And as soon as we reach F or G stars, we have late type spectra, very rich spectra, which are much easier to do spectroscopy on than these B stars with the broad lines. So our limit is actually the line width of S2. It's not the instrument.
That does depend on having a normal IMF in the center of the galaxy.
Yeah, okay.
We'll find out.
We'll find out that, yes.
Any further questions for Stefan? Do we have time for one more? With the ELT, if I remember, the top of the mountain is pretty much filled by the telescope. Are there any interferometric options with ELT, or is there simply no room to build outriggers or some way to increase over the?
No, I don't think so. Also, budget-wise, of course, it's the ELT is such that it's self-contained. And the mountain itself, Amazonas, is 35-40 kilometers away from Paranal.
Yeah,
that's too far. Yeah. So I think it would be more realistic to build a fifth telescope on Paranal, a fifth big one. But still, I mean, each of these telescopes is $500 million or so. It's not so easy to find it when you want to build an ELT. So I think, but also ESO realizes, of course, that interferometry in some sense is the life insurance for Paranal, because that's worldwide so unique that you will not give up on that, even in the era of the ELTs.
Great. Well, thank you so much. Let's give another round of applause for Stefan.